Hello, and welcome to the first Archeo Thursday webcast in 2013. This is Karen Mudar. I'm an archaeologist in the NPS Archaeology program. Today, I have the pleasure of introducing Dennis Blanton. Dennis is an adjunct archaeologist and former curator of Native American archaeology at the Fernbank Museum of Natural History in Atlanta, Georgia. He's also been the co-director or director of the Center for Archaeological Research at the College of William and Mary, and has spent a year creating and directing a new public archaeology program at historic Shirley Plantation. And his early collaborative work included investigation into the ways that severe affected the Jamestown colony in Virginia. Dennis has recently returned from 2 years in Costa Rica, and while he was there, he continued his research, focusing on the effects of climate and weather on Spanish colonial occupation of the American Southeast, including research on evidence of early Spanish-Indian interaction across southern Georgia and the entrada of Hernando de Soto. He also worked at the Costa Rican National Museum on re-excavations at the Las Mercedes site, a Chibchan site with ties to northern South America that dates to about 1000 to 1200 AD. Dennis also had a chance to work on various writing projects, so we will look for publications from him soon. Today, Dennis will discuss successful case studies documenting climate change in the archaeological and historical record. Dennis, thank you for accepting our invitation to speak today.
Well, thank you, Karen, for arranging the presentation, and hello, everyone. Let me ask before I go further if this is coming through clearly. For me, the opportunity to speak about this topic to a Park Service audience is meaningful, since it was early work at Jamestown that set me on the path to serious examination of climate, weather, and human events. In fact, I must say that part of what you'll hear today was made possible with National Park Service support, and other aspects were funded by the National Science Foundation. There will be three areas of emphasis today. The first is demonstration of some approaches by which past climate conditions may be reconstructed. The approaches I will highlight are somewhat novel, but they're also essential for a well-rounded portrayal of historical conditions. Secondly, my emphasis will be on the conditions in eastern United States, mainly because this is the area where most of my work has been conducted. But I hasten to add the same approaches tend to be appropriate elsewhere and have been demonstrated to be so in other parts of this country and the world. Finally, and perhaps most importantly, I will argue for the relevance of these reconstructions to the interpretation of past human experience. We must not slip into a trap of climatic determinism, to be sure, but we, as historians and archaeologists, overlook the fundamental role of climate and weather at our peril. Part of the opening background, it will be useful to clarify certain concepts and terms. Proxy data, I put that in quotations, provide indirect measures of past conditions in contrast to direct measures of temperature, barometric pressure, and so on that would be made with scientific instruments. Common proxy data sources are tree rings, ice cores, personal diaries, ship's logs, and newspaper accounts. Bottom line, for those of us interested in examining conditions beyond about 100 to 150 years ago, in the United States that is that there are exceedingly few sources of information beyond proxy sources. This makes the work challenging, but possible. We must also be clear about the distinction between climate and weather. Climate refers to longer-term atmospheric conditions, usually viewed from the perspective of millennia, centuries, or decades. Weather, on the other hand, means atmospheric conditions of the shorter term, measured in terms of hours or days, for example. Weather would also include relatively brief, extreme events, such as hurricanes and tornadoes. Let's also situate the case studies I will talk about in a longer global context. First off, there is some relevance to this subject stemming from the currency of climate change. Literally, a day does not pass when we're not confronted in the media by commentary regarding the issue. In spite of much misinformation, it's an issue that matters. And it's also possible to judge whether today's conditions, it is possible to judge whether today's conditions are unusual or not, only if we have a clear sense of what past conditions were like. So, what do we know about climate change over the span of many millennia and on a global or hemispheric scale? First, it's well documented that Earth's climate has experienced considerable natural change, and that much of that change is patterned. This is to say, over the long, long run, it's possible to document regular periodicity. The usual drivers of these patterns are natural phenomena, like varying levels of solar activity and changes in the character of ocean circulation. It's also true that since about 15,000 years ago, starting with the end of the so-called last ice age, or the Pleistocene, we also know it, the planet has undergone a net warming trend. This graphic illustrates both of those patterns. Working from left to right, over a span of about 400,000 years, an obvious sequence of alternating warmer and colder spells is depicted. Incidentally, this graph is based largely on ice core data. Incidentally, this pattern of regular fluctuation at about a 100,000-year interval is known as the Milankovitch cycle. Note also the steady upturn in temperature following the Pleistocene, and this is pointed out at the right-hand side of the graph. For our society, the pressing question is the extent to which human inputs have influenced the pace and degree of climate change. Few would deny that the latest warming trend is part of a natural cycle, but there is also some compelling evidence to suggest that our activities have created unusually warmer conditions. Again, this is not a debate we will enter directly today.
You have reached the recording limit. To record some more, press 5. To review your message, press 2. For more information, press star.
I don't know if this is me or somebody else. Can you guys check your phones? Thanks. Sorry, Dennis, please. Sorry, Dennis, go on.
You would deny that the latest warming trend is part of the natural cycle, but there's also some compelling evidence to suggest that our activities have created unusually warmer conditions. Again, this is not a debate we will enter directly today, but the kind of reconstruction we will examine do place the contemporary discussion into a context. And quickly, we can see in the same graph, and one other we'll see later, the rather extreme so-called hockey stick pattern at the far right-hand side, which marks an upturn in temperature.
Message left. Goodbye.
Pattern, has been central to much of modern debate. So, natural oscillations are a given, and in addition to the very long-term, low-frequency fluctuations that I've just described, it's also possible to discern briefer, higher-frequency patterns. Several examples of these events within the last few thousand years are more pertinent to the discussion today. One of these is widely referred to as the medieval warm period, or MWP. and it is roughly dated between about 1,000 and 750 years ago. As the name implies, this was a time of warmer than average temperatures. However, and importantly, we also know that it was not a time when temperatures everywhere in the northern hemisphere were uniformly warmer. In short, within that span, the MWP was felt differently in different times and different places. The same is true of another climatic interval known as the Little Ice Age, or LIA. The below-average temperatures of this span are real, but they were often expressed somewhat differently according to location. Finally, there is the interval that coincides with the modern era, and specifically following the Industrial Revolution of the 19th century. This we may refer to as the late Anthropocene, and as we well know, it characterizes another, but perhaps partially artificial warming trend. And this graph is here to help you see perhaps more clearly the expression of the medieval warm period and the Little Ice Age, and then also at the far right-hand side, the very sharp upturn in warming that coincides with the modern era. All of these intervals we've just discussed have been implicated as factors influencing the course of human events, especially in northern latitudes. The medieval warm period, for example, is argued to have created the conditions that resulted in a burst of cathedral construction in Europe. It also famously created the opportunity for Norse exploration and settlement in Iceland, Greenland, and Newfoundland. And I would argue developments like the Mississippian cultural fluorescence in the Midwest and Southeast of the United States were products in part of the same natural circumstances. Likewise, many attribute hardships of the 17th, 18th, and 19th centuries to the Little Ice Age. Certainly, I don't disagree, but most of us who make these connections also recognize that climatic conditions alone are not sufficient to explain the observations. They are simply one of the contributing factors. To summarize this background, we want to recognize that fluctuation in climate is an ongoing natural process. Further, we want to appreciate that the pace and expression of those conditions can vary within a given interval. And because most of the very long reconstructions are rather coarse representations of hemispheric conditions, it's necessary to document local and regional conditions with other studies. It is here that historical climatology, using proxy data sources, makes its strongest contribution. Also, we would be mistaken to extrapolate conditions reported from one location at a given time to another location, even during one of the named intervals. Instead, we must establish a baseline of historical averages and then investigate the extent to which conditions in a specific location are or are not deviating from it. In essence, that kind of process will be the basis for what follows in this presentation. Now we will begin a review of case studies from the eastern United States, and by and large from Virginia. And they exemplify the approach I describe as historical climatology. The first concerns a tree ring-based reconstruction of precipitation in southeastern Virginia and northeastern North Carolina. The use of tree rings to reconstruct past climate conditions is called dendroclimatology. It's important to understand that tree rings are most suited for reconstruction of precipitation patterns, and particularly those of the growing season, which in the east would be the spring and early summer. The methodological aspects of this kind of analysis extend beyond the scope of this webinar. But, suffice it to say, it is a complex and rigorous process when it is done well. Ideally, cores from multiple trees are utilized, and for each of them, precise measurements are made of ring widths, and sometimes other features as well. Ring measurements from cores from a given locale are then applied to create a single standardized data set, which can be calibrated against modern meteorological records. In other words, this latter step is a means of establishing whether and how individual rings behave relative to documented conditions, like rainfall. In the East, long-lived species conducive to tree ring studies include bald cypress, certain pines, red cedar, and oak. The featured tree ring case study today concerns what we now call the Jamestown drought. It was documented by a reconstruction that I made in the mid-1990s in concert with colleagues at the University of Arkansas's Tree Ring Laboratory. The project supported the National Park Service's effort to update the Jamestown story in anticipation of its 400th anniversary. At the time, I was a member of a research team composed of historians and archaeologists from the College of William and Mary and the Colonial Williams Foundation, working under contract for NPS to re-examine virtually every facet of the colony's history. A specific question, and to be honest, a rather scary question, put to us concerned climate conditions during and around the year the colony was established, or 1607. And trust me, achieving that kind of annual resolution, a single year, for most anything in the distant past, is a tall order. But, perhaps foolishly, I took special interest in the challenge. Ultimately, I proposed to the team that the only option for attaining single-year resolution was tree rings. My inspiration came in part from a successful tree ring-based precipitation history compiled by David Anderson, whom you've heard from before, I believe, for the area of South Carolina and Georgia. And he also worked with the University of Arkansas team. As it happened, the folks in Arkansas had already collected multiple cores from stands of ancient, living bald cypress trees nearby to Jamestown. But the cores had not been analyzed. Ultimately, we agreed to collaborate, and the result was an 800-year, high-quality record of rainfall. In these slides, you will see first on the left the method of extracting a core from a large bald cypress tree and the process of making ring measurements. One of the common questions we get is whether this coring process damages the trees, and I'm happy to say it does not. On the right, you'll see using a microscope the process of making those ring measurements. And here is an enlargement of a section of one of the bald cypress cores that registers 2 historical droughts. We'll talk about one of those. In this slide, you see at the top the EKG-like summary of the full reconstruction, with up or down shifts in the line recording wetter versus drier conditions. Below it is an excerpt that highlights the portion relevant to the early colonial period. We were startled, very frankly, when we discovered the close coincidence of severe drought and the 2 earliest attempts by England to establish colonial toeholds. With respect to Jamestown, it was one of those rare eureka moments. Suddenly, much about the legendary early hardships of the colony was more comprehensible. We had discovered at least one reason why. 7 years of intense drought between 1606 and 1612 made the expected challenges of establishing a colony into supreme challenges. No wonder there were reports of scarce food. The Indians they planned to trade with had little food to offer. Likewise, with descriptions of bad water in wells and in the river. Drought conditions, groundwater on the island becomes increasingly saline, and the same is true of the nearby river. Combined, malnutrition and poor water would certainly aggravate illnesses. And finally, now no mystery why the first so-called Indian War in the area was timed exactly with the drought period. Persistent demands of corn by the colonists surely became intolerable. In the bigger picture, the Jamestown drought turns out to have been a relatively localized event, limited mainly to the tidewater region. The same is not true of another drought we documented, the so-called Lost Colony drought of 1587-1589, and this makes reference to the failed colonial effort at Roanoke on the outer banks of North Carolina. At exactly the same time as the Lost Colony drought, the majority of today's continental United States was consumed by severe dryness, the magnitude of which is given it the label of a mega drought. Many instances of other local and continental scale droughts have been identified by the same process, and particularly in the East, it has amounted to a virtual renaissance in the study of climate and human affairs. At this point, we will turn to a series of case studies that rely on a different kind of proxy source, historical documents. This, you will have gathered, is a major reason behind that term, historical climatology. The first case studies will review relatively long-term patterns, and later we'll take a look at much briefer and more extreme events. What are the actual sources like? At least some are what I playfully call the records of founding forecasters, meaning those of luminaries like George Washington and Thomas Jefferson, among others. From a practical standpoint, it was in the interest of these large plantation owners to monitor weather. And more, from a philosophical standpoint, many of them were clear products of the Enlightenment, a time where a scientific approach to the world took hold. Later, in the 19th century, both plantation owners and smaller-scale farmers were inspired to make the same kind of observations under a progressive farming movement. I include this slide of Edmund Ruffin because he was one of those notable progressive farmers, in spite of the fact that most of us know him from his role early in the Civil War. Here is a slide showing the Plantation Journal of Shirley Plantation, one of the best we have and one that you'll hear more about shortly. Like the methods behind tree ring studies, the ins and outs of working with these documents are more than we can address here. At the very least, however, it's useful to say that while some are very thorough and lengthy, they're far from perfect. Measurements, when they were made, were taken from very basic instruments. The observers were not specifically trained as meteorologists, and their terminology was far from standardized. By the same token, they are often all we've got, and with diligence and care, especially when multiple records of this kind complement one another, they can provide invaluable information. Let's take a look. To reiterate, these data are especially important for documenting local and regional conditions. And we can first see how this has been possible with respect to rainfall. This first line graph combines comments about wetness and dryness from 7 different records made in central and eastern Virginia. Rather than measurements, the comments we're working with consist of diary or journal entries that literally include remarks like very wet, dry, severe drought, and so on. Simply put, the annual tallies of comments describing rainfall patterns become the basis for the graph. What we discover when the results are plotted as deviations from a mean pattern are, not surprisingly, brief spells of varying conditions. Alone, these results are perhaps interesting and helpful, but they become much more so against the backdrop of other and sometimes independent observations. But for the moment, try and remember what you see here, the indications of above-average wetness in the late 1820s, very dry conditions in the late 1830s and mid-1840s. From another set of journal records that pertain to the middle of the 19th century, we discover another spell of dryness, specifically in 1855 and 1856. Remember this one, too. Now we can test the veracity of these records by looking at how well they are corroborated by tree ring data and vice versa. Thus, in this graph, we discover that tree ring widths are registering precisely the same events. What is important here, of course, is that these comparisons elevate our confidence that observations made from one form of proxy data or another are genuine. But let's also remember that the main point of the exercise is to understand better the linkage between climate and weather and the human condition. This Shirley Plantation journal entry, we can make a clear connection between the two. Obviously, the dryness of the late 1830s had a host of effects. Some of them were negative and others were positive. At the top you see how it affected agricultural production, but at the bottom it also alleviated some of the issues of disease, particularly mosquito-borne diseases that plagued these areas at this time. Let's now use the same kinds of documents to record the incidence of extreme cold. Ordinarily, the Middle Atlantic is regarded as a place of moderate temperatures, but occasionally it has experienced different conditions. In the absence of thermometer readings, we can identify periods of extreme cold by making note of the occasions large bodies of water, like Chesapeake Bay and the James River, have frozen across. The commentary we rely upon in documents is of the same somewhat anecdotal nature, but it is likely that these attention-getting occurrences are almost always recorded, as a light rain, for instance, might not have been. Here's an example of such an account, and it is remarkable because very few people in this part of Virginia today could recall a time when this section of the James River had frozen to the same extent. If we tally all the comments regarding frozen bodies of water in Virginia and then rank them according to apparent severity, we certainly discover patterns, but what is most interesting is how they relate to other patterns. Before we go there, let's first review some other cold weather-related data from documentary sources. Here we see right away two periods in the 19th century with more frequent and severe freezes, one during the 1830s and another in the mid-1850s. We can also gauge winter conditions based on reports of snowfall. In Virginia, the 1820s appear to have experienced relatively moderate winters, while the 1830s are marked by above-average snowfall. As before, we can use tree ring data as an independent basis for checking the patterns. But in this case, you're looking at measures of tree ring density as opposed to tree ring width. Densities are an indirect indication of temperature, high density equaling relatively cooler, and the opposite for low density rings. Lo and behold, we discover in the northern hemisphere virtually total corroboration. Ring densities are also telling us the late 1820s were milder, but the 30s and mid-50s were unusually cold. About now, you should be recalling that these same blocks of years were also marked by anomalous rainfall patterns. How do we account for the relationships? As indicated on this graph, it's very likely that El Nino, or ENSO conditions, were influencing the milder and wetter period late in the 1820s. I attribute the cold weather spells of the first half of the 19th century, generally speaking, to regional expression of Little Ice Age conditions. Others have come to the same conclusions looking elsewhere. In other words, the LIA seems to have been most pronounced in eastern North America at this time, in contrast to Europe, when it was more apparent at an earlier time. Before we contemplate the wider implications of these cases, let's look at one more category of information, this time related to growing season length, clearly a matter of relevance for agricultural economies. I've done this, again using diaries and journals, by recording the last mention of hard or killing frost in the springtime and the first mention of the same in the fall of each year. The number of days between those dates provides a rough measure of growing season length. This graph summarizes the results using the Shirley Plantation source. We see what is by now a familiar 19th century pattern. Here, as longer than average growing seasons in the 1820s and shorter ones in most years through mid-century. But the shortest seasons are occurring in parts of the 1830s and 1850s and also the 1840s. To summarize this part of the presentation, I believe we can agree on certain tendencies. In so many words, it was a better time to be a farmer in the 1820s than it was in the 1830s and 50s, and probably also the 40s. All in all, then, the second quarter of the 19th century in Virginia was difficult from a climatic standpoint, in part because little ice age conditions were strong. But all things considered, the 1830s were the obvious low point. Life must have been very difficult, plagued as those many years were by the combination of drought and cold. How might we test this suggestion? This graph provides one measure of the effects. In short, it's no wonder tobacco prices were stable in the 1820s, but experienced sharp spikes in the 30s and 50s. More broadly, I will propose the more difficult years, climatically speaking, were a factor in events like the infamous economic panic of 1837, when we're told explicitly in some cases that there were crop shortfalls, and also the westward migration that the country experienced. The last set of case studies involves extreme weather events. These would be short-lived phenomena like tropical storms and tornadoes, but also the effects of phenomena like volcanic eruptions. Although short-lived, these events, as we are well aware, can be very powerful and result in huge economic impacts, not to mention health and safety hazards. Once again, we must rely almost exclusively upon proxy documentary sources to understand the events and their longer-term patterns in the period before about 100 or 150 years ago. Let's begin with a reconstruction of the Great Flood of 1771. At Richmond, Virginia, which has experienced its share of flooding because it's located directly on the James River, at the fall line, this flood is accepted as the highest and most destructive ever recorded. The flooding was also experienced over much of the eastern seaboard in association with the same weather event. I must be brief here because of our time limits, but in short, our examination of many historical documents revealed not only the very wide extent of flooding, but also, in great detail, the life history of a powerful but slow-moving tropical storm system. Using a network of accounts consisting of ship's logs, diaries, newspapers, and so on, we could chart the movement of the storm system from north to south in the flood crests in the rivers as they moved from west to east. Ultimately, at Richmond, the flood crest was measured at 40 feet above the normal level of the James River. You see at the top here, what the normal flood pool of the James River is like, and then below it, what we estimate to have been the conditions at the height of the 1771 flood. Remarkable change. Even the well-documented severe flooding associated with 20th century Hurricane Agnes did not quite eclipse the 1771 level. All told, it was an epic flood. And that flood inspired all manner of actions. In one case, a large stone monument was erected at the high water mark below Richmond. Still stands there today, largely forgotten in the woods. The inscription from it you see presented in the slide here. And I'll take a moment to read it. It's a very powerful statement. In the calamitous year 1771, when all the great rivers of this country were swept by inundations never before experienced, which changed the face of nature and left traces of their violence that will remain for ages. The severe damage of the flood, not only to property within the city and beyond, but also to the agricultural economy, led the colonial leaders in Virginia to draft the very first disaster relief package in the country, acknowledging grave impacts to both the wealthy elite and to the less privileged alike. Another legacy of this flood were new city plans throughout the East aimed at keeping certain properties above flood levels. We usually don't associate the eastern United States with threats from volcanism, but there are cases when very powerful volcanic eruptions do assert some effects. When they are felt in that region, it's usually as a general cooling of temperatures caused by the introduction and then dispersion of massive amounts of gas and particulates into the atmosphere, acting to diminish the sun's warming. One fairly recent example was the effects of the Mount Pinatubo eruption in the Philippines. Here you can see from this first slide just the extent of the gas and ash that's pushed upward into the atmosphere. And then in the aftermath from this slide, you can see how those particulates and gases are collected and dispersed around the planet. For our purposes, the signature events occurred in 1816, or the famous year with no summer. In actuality, it was in April 1815 that the Indonesian volcano called Tambora experienced a massive eruption. By the next year, global climate was affected noticeably. Europe and Asia were reporting crop failures and famine. In the United States, crop failures were widely known, particularly having occurred in the northeastern United States. As I began to reconstruct the patterns of weather and climate in Virginia and neighboring areas, it also became apparent that Tambora also had an effect farther south, which was something that hasn't been noted before. In the Shirley Plantation Journal, for instance, there was this entry. Shirley's farmers might have been oblivious to the cause, but they were very clear about the effects. Indeed, it is obvious the memory of that disastrous year lingered for at least a generation, as the following 1835 entry shows. And incidentally, make note here of how different eruption might have been partly responsible for some of the coolness we've discussed in the 1830s. Before we move on, we can revisit this graph of tobacco prices, and I believe see clearly some very real economic implications of these distant eruptions. I've indicated timing of the two in red on the graph. You can see the correlation between the upturn in prices. It would be easy to go on and on about the general topic of climate and even about the specific cases from the East. But I trust these few examples have provided a flavor of the issues, the process of research, and some of the implications of climate and weather for people. By way of conclusion, I want to give emphasis to a few take-home messages. First, climate and weather combine to produce large and fine-scale patterns. Proxy data sources inform best on local and regional effects. Climate and weather do influence human events, but the strongest effects of climate and weather usually occur in tandem with other stresses of both a natural and a cultural origin. It is this final point that warrants just a bit more discussion. It is the exception rather than the rule to find that climate or weather alone have caused significant or lasting impact in human affairs. When that is the case, it is usually in the aftermath of short-lived but very severe events, the instances of floods, hurricanes, and so on. Most of the time, climate and weather have lasting impacts when they create stressful conditions that exacerbate other stressful circumstances. The effect is a perfect storm of challenges. The Jamestown drought loomed large only because the fledgling colony was also suffering in other ways. The economic panic of 1837 was only aggravated by crop failures and their effects on prices, and so on and so forth. Thus, climate and weather extremes are among the factors that become tipping points. From the standpoint of human activity, we can't appreciate them in isolation, but we also can't ignore them. This has been true in the past, and I dare say it will be true in our future. Thank you very much. And before we close, I have a couple of slides here that will provide you with sources of additional information. It's a big topic. It's one that has been addressed widely. If you're intrigued by it, you might find it useful to, or if you find it useful to consider in your own work, here are a few websites to examine, and then also pages of additional readings. And with that, I'll thank you for your time, and we'll be happy to entertain questions.
Dennis, thank you very much for that very interesting talk. Do people have questions?
I do, but I don't want to ask.
Can you speak up? Oh, I thought someone had a question. Well, I have a question. Dennis, can you explain to us why does tree ring density increase? And what exactly are you meaning by density? Is it cell density?
That's exactly right. It's the cell density in the trees. And the short explanation is that when climate conditions are optimal, the trees are drawing the nutrients and moisture from the ground through very large active cell networks. When climate conditions are less optimal, the trees undergo a certain level of dormancy, and so that cellular structure becomes denser.
Ah, okay, thank you.
Hello?
Yes?
Hi, Dennis, that was an incredibly interesting presentation, especially since this is Julie Steele. I'm at Petersburg National Battlefield, where I know you did some work, and I'm very familiar with a lot of your work. Going to really use some of this. I wonder if you've ever tried to put data related to epidemics along with the climate stuff.
Yes, that's a wonderful question, and historical climatologists, epidemiologists have worked together to try and measure the correlation between the effects of climate, of course, and diseases, particularly mosquito-borne diseases. There have been a lot of studies that you could discover online that attempt to correlate wetter and warmer conditions with outbreaks of infectious disease like yellow fever, mosquito-borne diseases, I say. We looked at this in the area of Norfolk and Portsmouth, which experienced more than once in the 19th century very severe outbreaks of yellow fever. And the patterns that we discovered, frankly, were there. I mean, in other words, there was an indication of warm and wet conditions conducive for breeding of mosquitoes, but they weren't exceptionally unusual. In other words, they wouldn't have shown up very, very clearly in the kinds of graphs that you've seen today. So this is a case in point that there's more to it than simply weather. The weather conditions have to be appropriate, but other things are at work as well. And of course, it has to do with sanitation and drainage within the cities, and then the introduction of the disease in the first place. In this case, it was ultimately traced to passengers on ships.
Yeah, I guess once it gets established in an area, it'll then spread out no matter what the weather is. But
well, that's just about right. As long as the vector can make it, then it will spread, sometimes frighteningly quickly.
Interesting. Thank you.
Thank you for the question.
I have a question. This is Marcy Rockman, and Dennis, I was one of your students at William & Mary, so this was a great joy to hear you talk again.
Hello, Marcy. Great to hear you.
Thank you. I so much that's fascinating, and I have a pile of questions forming in the back of my head, but the one I can articulate at the moment is fascinated by the social memory of weather events, and that the reference that you noted in 1835 back to 1816. In the records that you've seen, are there many references to previous events or comparisons back and forth, or do a lot of records tend to be fairly objective, just this is what it is now, and not comparing it to what they've previously experienced?
There are common references to some of these events. The year of 1816, of course, was referenced more than once. It became the standard against which other dry periods and other difficult summers were judged. The same is true of flood. The 1770 flood is one that was mentioned routinely. But the pattern, and this is my sense of it because I haven't looked at it in the same way you're suggesting, is that the duration of that retention is probably a generation or two. And that would only be in association with truly catastrophic events.
Okay.
Now, the legacies of those may remain. In other words, if cities enacted new planning ordinances or something like that to prevent flood damage, that's a legacy, but it's not in the same common memory. It's become an official aspect of life as opposed to one that's conjured up, or provoked by another flood necessarily. Which is very interesting. I wrote an article about the 1771 flood, and of course it's fascinating working with hardcore climatologists and things, and we had great fun recreating the life history of this tropical storm, but for me ultimately it was about the people, and one of the messages that I tried to make in that article was that First of all, these extreme events affect most badly the indigent or the poor, and they're the ones often left with the least help. But also what's fascinating, and we compare it with some of the great Mississippi River floods of the 20th century, people don't necessarily change their ways. I mean, I mentioned that cities in the East had adopted new planning ordinances and so on, but you know what? People just don't change their ways very easily. They'll go back to settling in areas that are vulnerable to flood or other kinds of catastrophes. And that's a fascinating phenomenon that, in fact, some sociologists have looked at.
Thank you very much.
So I would encourage you to pursue that line of study. Well, they're like so many things. We recover from the initial impact, but we don't always have the political or social or personal will to make hard decisions that require large-scale alterations of our lives and infrastructure.
I've been putting a few examples together of learning versus not learning, so you've just added a few more lines to my list.
Are there any more questions?
Hi. You mentioned the 1838 panic. I was wondering, it sort of looked like your data might also line up with the 1857 panic. Is that accurate?
Well, I think so, and we have to be cautious here, and I would say yes. I suspect that that period was another one of those intervals of those perfect storm, we'll call it one of those perfect storm scenarios, when there was this conflation of factors that created all kinds of stress and hardship. I haven't looked specifically beyond just general knowledge that was the case into the cause and effect there. But I think there's a very strong possibility that this was a contributor. I also mentioned westward migration. And, there again is a case in point where, sure, weather was probably contributing. But it was probably contributing only if people were suffering or struggling in other kinds of ways, which we knew they were. And it varied, of course, from place to place, person to person, family to family. But let's say you were one of the many, many farmers in Virginia or any of the original 13 colony states where soils had been depleted, population had risen so that opportunities for new land and so on were reduced. Then if you had a bad crop year or two or three in succession, it would be, I think, a good cause for most of us to consider and maybe throw in the towel and seek out greener pastures. So, again, it's most likely one event and one important event, but weather and climate wouldn't be the only ones.
Thank you.
You're welcome. I think these questions are wonderful ones, and I think they're testament to how much is possible to do beyond the work that's already done. I'll say that climatology, of course, is the bailiwick of climatologists. And when I first started this work at Jamestown, for me it was questions regarding conditions associated with the colony. But I had to rely on expertise from others like the tree ring specialists in Arkansas. And I'll never forget, and it's affected my approach to this all along, is that I had a conversation with Dave Staley, who's at the tree ring lab there, and he's a climatologist. And I was talking to him about how he got into this line of work. And he said what I really was feeling at the same time. He says, I want to do something that's relevant. And, of course, all of us in our professions probably feel that way. But sometimes as an archaeologist, it's difficult to feel that way. And this was an area that, for myself, turned out to be one I thought I could make a real contribution. Not only was it helping us as archaeologists and historians to understand particular events and periods of time, but it also was contributing to the larger debate about climate change, because what I learned was we can debate until the cows come home about the effects of our activities on conditions and carbon loading and so on, but we must have long-term records to judge just how unusual our modern conditions are or are not. And that's what these proxy data sources do for us. So ultimately, we're making a contribution on two different fronts. I've found it very, very satisfying for that reason. And if any of you are interested, it's the sort of thing you can do as well. Say you're at Petersburg or anywhere else in the country, if you can search out diaries and systematically collect that data and do that from multiple sources, you can probably do exactly the same thing.
Well, Dennis, this is Karen Mudar again, and this has been a wonderful presentation, a great hour. I was not aware at how complicated understanding climate variability could be. I was impressed that you looked at so many different sources of data and you were able to look at the interactions between things like volcano eruptions and so events to give us a more detailed picture of climatic variation. So I really appreciate your talk today and have thoroughly enjoyed it. Thank you very much.
Quite welcome. Thank you.
Thank you.